So I neglected to mention back when we discussed Bussy spaces, I didn't quite expound upon actually constructing the topology of that space, right? Because the Bussy space is either a vector space or a topological space. And if we're talking in terms of the topological space, we need a basis and we need a topology for that, right? So let's redefine the Bussy space by first discussing or constructing it from its basis, and then its topology, and equipping the original set with the topology. Um, of course, here in this video, we're gonna continue the notion, or we're gonna continue to use the notion of an intersection between two sets that are tangentially or directly related to it, so it may be slightly related, and it's guaranteed that their intersection is absolutely the Bussy set of those two, or it's the Bussy set itself. Now, the Bussy set is an arbitrary thing, if you think about it, or from all that we've studied, we know that the Bussy set is itself arbitrary. It can be an arbitrary amount of things. It can be a thing, it can be an ordinal, it can be something like that. So I suppose today we will be formally defining what exactly the basis is. Because when we construct a topological space, one of the most important things that we have to do is construct a topology, of course. And when we construct a topology, we need to define its basis. So consider another footnote in a much earlier segment of this course. So let's start with what exactly is a basis. So definition, a basis is a set which I will call B, set B. No, it's a collection of subsets of A such that one, the union of all B in B, so all elements in B, which is all B. So whether it's ordered or not is precisely A. So the union of all these subsets of B is A. So it's possible that the basis of A is its power set, because when we take the union of a power set of A set, we get B set. That's one qualification. And in fact, the power set of A is precisely its discrete topology. Okay, so the second condition is that given two basis elements, so given a B1 and B2 inside big B, and an A that's inside, since these guys are like subsets or are sets, I'm not using the subset notation here, because right now we're dealing with the most elementary of notions. We're working at axioms here, and the notion of a subset like this is a non-elementary notion. So we're using epsilon, or we're using the set membership, or this membership symbol here for elements, for sets. So it's not restricted to elements now. It can be used for sets, because a set is inside. So without using subset, what it just means is that it's inside it. So it's inside the intersection between B1 and B2. So there exists a B3 such that A is inside B3, which is inside B1 intersection B2. So if I have two sets inside the basis, so I have two sets, and I take their intersection, there is another set B3 that's inside this intersection, which some element A is inside the intersection of, the primary intersection is inside that set. So I have two elements, and then this is their intersection. I can make a subset that is precisely B3, and then there is an A inside here. That's A. And so this over here is the if this is B1 and this is B2, this is the intersection of B1 and B2. So that's the picture of this condition. So yeah, an example of this so there are mainly two types of this, called discrete and indiscrete topology. So the basis for discrete topology is just all open sets, I suppose. All open sets inside the power set. So every element E of the power set of some X, X is set, open. So that's our basis. So every E. So this is the basis for that generates, we say, the discrete topology on X. And every element E such that E in X open is the basis that generates the indiscrete topology. So this generates T equals power set, the topology must contain the empty set and X. So empty set X and P of X. Because you notice that the intersection of all these E would precisely give us X. Right? And since they're open, we can, even though they're not open, if they're closed, we would still be able to find a subset inside an intersection between two sets of this set, and then we will be able to find a point inside that set, which is inside the intersection between two other sets inside this big set. Okay, so that's our topology. And then, so this would give us a discrete topological space. In our case, if these guys are subsets of this, of course, then X is a set that's X is constructed from an intersection between two sets that are tangentially or directly related to Bussy. This would give us the discrete, or this would generate the discrete topology over discrete topology, or the discrete Bussy topology, which would generate our discrete topological Bussy space. Now this one over here, is what generates the topology. Of course, empty set X, and that's it. Actually, this is it. And that is the indiscrete topology. And this equipping X with this topology, like when we do this, we equip this with X to obtain discrete topology. This one would give us the indiscrete topology. So we don't specify exactly what the subsets of X are. We just say that it is just X, the entirety of X. Like if you can express X, of course, as a set, then that'll be great, because we'll be able to still somewhat define open balls in the indiscrete topology. So this would generate just equip our original Bussy set with these topologies to obtain the respective topological Bussy spaces. So, yeah. Now, another one I want to take note of, especially after our recent developments in mathematics in our curriculum, is the Euclidean topology. So you guys recall about R, and maybe even FR. Of course, FR is the set of all Femboys that have a bijection with the real numbers. Now, you'll notice that every time we take an intersection between two Femboys, it is obvious that their intersection generates a Bussy set or a Bussy space. So it's not too far off to actually use the metric topology and respectively the Euclidean topology, and they construct a topological space from there. Right? What we can do, we already have a bijection between each f in R. So if I have some subset of f, it will certainly have some respective subset in R which have the same cardinality and stuff like that. So that means we can still employ the Euclidean topology on that, but we just have to sort of half it there, to make it conform to that. Maybe even mod it out. So it's like maybe R mod something, and then we would split the topology at the nth open element. And the basis is just every subset there. Of course, it just seems like it's needlessly, or constructing a basis needlessly complicated, because when we discuss topology at first, or when we first learn topology, we want the notation to be as compact as possible. So sometimes we just sort of express it as these intervals and then the intersection or the union of these intervals. And that may look a bit jarring or a bit complicated to someone new to topology. But it's all the same idea. It's just all subsets inside the topology. Because when we take the subsets or all possible, the union of all those subsets, we get the set. And that satisfies the first criterion for basis. So the basis could be the entire topology of a set, because when we do have a topology, it would contain the set, the empty set, which almost every set contains, and of course the elements of that set. So when we take the union, that X, or the set X itself, is absorbed. Or if it appears like we have excess copies of an element inside, or of any element inside our original set, when we take its union, it becomes one set. And according to the definition of sets, it would absorb those. Or it would absorb those excess elements. So alright, the Euclidean topology. So a metric topology is associated with a metric D, which takes two inputs in our space and then maps them onto R. So it assigns a distance, you could say that's why it's called D, and our way of formalizing that in topology is via an open ball, which we denote by B, alpha. Alpha is like an index. Or D, sorry, not alpha. D, and then at some base point x and radius epsilon, and this is all y in our original set x, such that the distance between some center point x and y is less than epsilon. So this is all points y in x, such that x, the distance between x and y is less than epsilon. If we say it is equal to epsilon, this generates a closed ball inside. But we're only concerned with open balls because right now that's our way of defining continuity and stuff like that. So let's say that X is a Bussy space, right? So I have two sets that are much bigger than R, and then I just take their intersection, and then that intersection so happens to generate a Bussy set. What I just have to do is equip or generate a basis. So I'm gonna construct a class of all these open balls, and that is of course such that X, the center point, is inside our original Bussy space X, and then epsilon greater than 0, because there's no such thing as negative distance, even in our theory. So this over here, this subset or this space or set of open balls of base point X and epsilon, radius epsilon, is precisely the basis for the Euclidean topology. I mean the metric topology. It's the metric topology on X. So this is the third topology I want to define. The metric Bussy topology. And finally, the last one to end the lecture is the metric topology. So because we have a bijection with R and right now we're assuming the X has a bijection, the Bussy set has a bijection with R, Xn is certainly bijective with Rn. So we can construct a Euclidean metric, perhaps. I know that it's possible that Xn might have a bigger cardinality in Rn, and it would be an injection, not really a bijection. But let's just assume that yes, it stays the same cardinality as Rn when we take its product, of course. Now this would assume a product topology, which is basically the product topology, which I will call like this. It's just to set all mu cross alpha such that mu, if I return my favorite picture on the product topology, so yeah, all mu and alpha such that mu and open in A, mu and open in B, and alpha open in B. For some, product A cross B, and then we want to construct a topological space from that. So this product A cross B with this topology would precisely give us the product space of A and B. Okay, likewise, what we want to do is define the Euclidean metric from this. So I mean that's another thing. If I have two Bussy sets, right, and I take their cross or their topological product, it would imply this. So if I have a product that's constructed from two topological Bussy spaces with already a predefined topology, this would be its topology, and of course the basis would be all possible subsets of this, or all possible subsets of that topology. That's the basis. Okay, so I have current metric, so Xn cross Xn, and takes it to R. So any amount of dimensions, and then we use some notion of distance that we define between them. So the standard topology on Xn is the topology generated by the Euclidean metric. So our distance function is undefined at the moment. We don't know it at the moment, but let's define it this way. So the norm of x minus y, which is also equal to the sum of all n of xn yn squared. So this is the Euclidean metric. So this is one way of defining the metric, because right now, before I wrote this down, the metric that we have defined is arbitrary. It's not quite well defined just yet, and it could be anything you guys can say. It could be like 1, it could be 2, it could be whatever. Right now we have a function that I assign to that distance function that defines it, and this is the Euclidean metric. And it makes sense because the distance function is precisely this. I have one point, I have another point, and then I just take the distance between them, or find the distance between them, which is this over here, which is like if I have the x and y components, I mean x1 minus x2 squared plus x2 minus y2. I mean y1 minus y2 squared, and then take the square root of that. You know, you guys know, elementary. So yeah, if we assign the distance function to be this, our topology now is the Euclidean topology, or the standard topology. Yeah, this is the Euclidean metric, and then we have a standard topology. So that's our standard topology, and that's our standard topology on the Bussy space. And so that's what I wanted to lead to. So that's the third and last one that I want to define in this video. Now there are many more topologies you can define over a Bussy set, but this is just a couple of them. So yeah, that's it. This is a good place to stop.